N-type and P-type semiconductor in contact, then at its interface, it will automatically form a so-called building electric field at the interface. Okay. So let me ask you one question. On the left-hand side of the semiconductor is boron-doped silicon. All right? On the right-hand side is phosphor-doped silicon semiconductor. What I want to ask you is, which side is the N-type semiconductor?
Left side.
Left? Raise your hand if you think that is on left-hand side. N-type. Okay, put down. If you think it's on right-hand side, please raise your hand. Okay. Oh, still someone. Okay. Okay, let me think about that. N-type, I'm talking about N-type. So N-type, we want to create electrons, right? So we doped the element that have more valence electrons than silicon. So we need to dope group 5 element in group 4 silicon crystal structures. So we need to dope phosphorus for N-type. So on the right-hand side is N-type, nothing in the left-hand side. Okay, so you have to take a look of the yesterday's handout. You see? This is N-doped. I'm sorry, I may put it wrong. This should be P-type. All right? So correct your notes on page 15. This is P-type. I may misled you, sorry. For semiconductor that dope with group 5 element, that will be N-type. But for silicon semiconductor, if we doped the element in group 3, for group 3, then it will be P-type. I'll change that with P-type. So the Fermi level will be very close to the valence band edge. So when we go to the p-n junction, now on the right-hand side it's N-type. On the left-hand side is P-type. All right? Okay. But how come I write all positive charges in N-type side of a semiconductor? That is because when I put the two types of semiconductor together, they are charges diffusing each other. Okay. On the N side, right-hand side, that is N-type, right? So N-type has lot of electrons. On the left-hand side is P-type. There's a lot of holes. All right? So electrons and holes are mobile charges. They can move everywhere. So it is different from immobile charge. Immobile charge is the ions that's made of the crystal structure. That is building the crystal structure. So those ions cannot move. This is a charged ion, but it cannot move. This is a main frame. It's a framework of the crystal. Only those mobile charge that can move. Mobile charge are two kinds of charge, electrons and holes, right? For those charged ions like phosphor plus or boron minus, they are not movable. So it's immobile. Even though they are ions, they cannot move. Unless you use very strong electric force, then at that time you will break down, you will damage the structure if they move. All right? So I'm talking about the mobile charges, electron and holes. So On the right-hand side is N-type. Since N-type, it has a lot of electrons. On the left-hand side, it has a lot of holes, and it has, since it's P-type. So when I put two semiconductors in contact, electron and holes will diffusion. You know the diffusion. Diffusion will do the flowing from the high concentration to low concentration area, spaces. So since N side sees the other side has no electron concentration or hardly any electron concentration, so electron will flow from right-hand side to the left-hand side. On the other hand, hole will move from the left-hand side to the right-hand side. So they will diffuse. Now, however, the diffusion will not go on indefinitely, because when electron and holes diffuse, they will leave immobile charges at the interface. You see? Actually, there were electrons also here in this so-called depletion region. I would explain the depletion region later on. There were still electrons before contact. It's all electrons. The electron seeds covers all the framework of the crystal structure. Now, just like this part, like neutral region. However, when electrons diffuse from N side to P side, the electron will reduce the boron, so that boron get a negative charge and become immobile ions. So they will combine with holes. Hole and electron will exchange each other and leaving the unattended immobile ions. All right? So what I here said, positive charge or negative charge, is not the mobile charges. This positive charge is the immobile charges that is exposed if mobile charges are diffusing to the other side. All right? So when diffuse occurs, mobile charge diffusion occurs, then they will expose the immobile charge. So we will see there's a charge appear at the interface where N side has positive charges, and in P side they are negative charges at the interface. Can you understand? Okay. So, and here is neutral, because even though this is ionized, but there's also always electrons in nearby. The electron can flow back and forth, but they are nearby. So this is called the neutral region. Although there are a lot of electrons, but it's electrically neutral. All right? Can you understand? Any question? Okay, very good, very good. Because this is most difficult part of the semiconductor, because a lot of students may stuck here during his study of p-n junction. Actually, here is neutral. Even though we did the N-type doping, it's still neutral. Even though we create electron mobile charges, it's still neutral. It becomes positive charged when the electrons are diffusing to the other side and expose the immobile charges. Then it becomes not neutral. Also, the same thing. When holes diffuse to the other side, it combines with electrons and exposed the negative charge, the immobile charge, that boron ions. So it becomes charged layer. And the place where far away from the interface is still neutral. I will show you why it will keep it neutral. There are a lot of holes, mobile charges, protecting those negative charge ions. So it's neutral. All right? So if diffusion occurs, if a mobile charge occurs in between, crossing the interface, they will expose the charged immobile ions. The immobile ion will create an electric field. The electric field is acceleration direction or the force exerted on a positive charge. All right? So if you put a positive charge at the interface, which direction do you think the positive charge will go? A positive charge. If I put a positive charge just at the interface, a stationary one, I put here. What do you think the direction? Left. Yes, because you want to go to the negative, and they don't want to get on with the positive charge. All right, so they will go left. So the field is to the left. And what is? Oh, thank you. Okay, if I put the positive charge here, it will move to the left. Very good. Okay, so what if I put a negative charge like electron? Which direction it will go? To the right. Yeah, the opposite direction. Okay, so if I put the electron here, this field will force the electron to go to the right-hand side. All right? So it is against the direction of diffusion. See? The electron, for the diffusion, if the driving force is diffusion, it will cause the electron to diffuse across the interface to the left-hand side. However, during the diffusion, it will expose those unprotected ions and form a built-in field. And this built-in field will build up gradually and against the further diffusion of the electron from right-hand side to the left-hand side. So this force counterbalance each other, and eventually they will reach equilibrium. All right? Okay, this equilibrium will be formed because this diffusion actually causes current. So when the p-n junction we put p-n junction in contact together, there will transient current occurring during at the time when we contact them together. But this current will not produce continuously. All right? We don't have these good things. If this does happen, then we have electricity always. So this will not happen. Just transient, for very short periods of time, this will happen. Eventually, they will become equilibrium. The equilibrium is caused by the interface, the building field that exerts a force against the diffusion. So eventually, the depletion region. What is called the depletion? Why is it called depletion? Depletion is called all the mobile charges are depleted in this region. So there's no more mobile charges like electron and holes. Okay, so as the diffusion proceeds, the depletion region will also develop to increase its width until at a certain point the equilibrium is reached. Then it will form a width, depletion width. And this depletion width can be calculated. There's an equation, and it's a function of doping of both sides, and also as well as the band gap of both sides. Okay, but I do not have time to go into detail of the equation. I just want to let you know physically what happened at the interface. So at the interface, there were depletion region, and outside the depletion region, there are neutral regions. Okay, so this is what we usually draw for the PN junction. For P-type and N-type before contact. See? Now you know this. You know what does this mean, right? I draw the band diagram. For P-type semiconductor, we have Fermi level very close to the valence band. Actually, the Fermi level will depend on the doping concentration. The higher doping concentration, the more closer of the Fermi level to the valence band edge. And even they will exceed the valence band edge when it is degenerated. Okay, and this is representative of the energy band diagram of N-type semiconductor. When we put them together, then the energy band diagram will be something like this. This is very intuitive. You will be able to know that from the perspective that the Fermi level actually is the sea level or water level of the electron, right? So for these two materials, they have different sea levels, just like some land that's separating to sea. If this sea has two levels, that doesn't matter as long as they are separated. However, if you want to build a canal between these two seas, then you need to find a way to balance this two sea level. Otherwise, they're always the water flowing from one side to the other, right? This is exactly what happened in the PN junction. When we force them to contact to each other, the sea level have to be the same. Otherwise, you still need to have something to separate it. But since you connect them together, they are not separating anymore. So they will adjust each other until the Fermi level are at the same height. All right? So how they adjust this? Just because of this, we just mentioned about, because we build an electric field that will change the potential of each side, so that they will have V no and QV need.
Good morning.
Okay, have a seat. So they build an electric field in this direction. And this electric field will build the potential of N side higher than P side. All right? The potential is respective to the positive charge. But in terms of energy for electron, this side will be lower. The electron energy of N side will be lower than the electron energy of P side in the conduction band edge. All right? So in this view graph, I just want to show you when two PN junctions are in contact, they will adjust their Fermi level until the Fermi level is the same. So the conduction band edges as well as valence band edge will have it's not like discontinuity. They will have a transition at the near the interface. Actually, it's in the depletion region width. That will be a transition at the depletion region, so that energy level will be different for electrons. All right? And the energy you can see that this one is about the opposite side of the the potential, right? Because the potential is respect to the positive charge, so it will go this way. But for electron is negatively charged, so the energy is reversely the potential, but plus a Q, a charge, QV, no. All right? So?
If we increase the doping,
Yes.
P-type and N-type, the electric potential will be increased.
If we increase the doping, right? Increase the doping, yes, the electric field.
Limit to stop there.
They are a function of doping as well as band gap, and the doping between the difference between two sides. So that is a little bit complicated equation. Let me see if I prepare the equation for you. No, probably not, but it's easy. Well, you can find the equation from all the textbook. If you are interested still, then I will show you in the break. All right, it is a function of doping of both sides as well as band gap of both sides. Sometimes the P-type and N-type semiconductor are different semiconductors. They are not always necessary to be silicon. They can be different. Okay, so let me go back to this page. So basically, if you dope, then more heavy, the voltage drop. The voltage will be higher. You can see this is just qualitatively mention this. If you doping this to more heavy, the Fermi level will move further downward, going down, right? And if you dope the N-type more heavy, they will go up. So when they contact together, yeah, the separation will be much higher, So when you doping higher, then the voltage, this voltage will be higher. Yes. Okay. So now we would like to find out what will be the diode equation. Diode equation is the equation that describes the current and the voltage relationships when I bias the PN junction. Okay, when I bias the PN junction. So let's us take a look of the PN junction. When it is not biased, then there will not be bias field because I am not biasing it from externally. So it's no bias field. But there will be always built-in field inside. The built-in field is toward left. Okay, you need to have the feeling about that. So maybe memorize that in this class. Now, if I put so-called forward bias, the forward bias is to bias it externally, but put the positive charge. Just I use another battery to charge this PN junction. All right, with positive to P and the negative end to N. This is called the forward bias. And if I use external battery to charge this PN junction, but put the negative side with P and the positive side on N, this is called the reverse bias. Okay? For positive charge, for forward bias, since we connect positive this side and negative this side, we build a field from positive to negative, as we defined earlier, right? So this field, the bias field, will against its built-in field. They will counterfeit each other. And for reverse bias condition, we will build a field that is in the same direction as built-in function. So the field will add up. These two factors will add up. All right? So this is a simple representative of phase band energy diagram as well as potential, the voltage potential diagram for three conditions. In the middle one, in the leftmost one, it's unbiased. Unbiased means no external voltage applied on the p-n junction. So this is case where we know first the p-n junction, the automatic built-in and built-in function. So this, and they have Fermi level aligned. So they have built-in potential as well as energy difference on the conduction band edge as well as at the valence band edge. This is the equilibrium condition. Now, in the middle one, this is forward biased. Forward biased since against it, right? Yeah. The external bias, the field is against the building field. So it will compress the deposition region. So the deposition region the width becomes smaller, and the voltage difference between p-type and n-type will be smaller. Okay, and at the same time, the Fermi level is separated by the external field. And the separation of the field is exactly the same as the external bias voltage times QV. All right? So that now the distance between the conduction band edge on P side and N side will shrink to V naught minus V forward, VF. It's not very clear, but I will have a view graph shows much clearer characters later on. So it will shrink, and the reduction, the amount of reduction is exactly the voltage of externally applied, times Q, right? And for the third case, which is reverse biased, for the reverse biased condition, those two fields add up. So it will increase the building field. It tracks the mobile charges from the interface. So the interface will will develop more. So it will be something like this. And the increment of the energy will be Q times the reverse biased V. So the total difference now increased to QV naught minus VR. And we put minus it because VF itself is negative. All right? So actually it's increased.
End to end.
Huh?
So they repulse from the middle?
Yes.
From the end to end.
Yes. Yes. So this is qualitative. It's a very good qualitative representation of the condition for p-n junction under bias. Okay. Let's go to the previous one.
So usually this we have using it in diodes.
Diodes, yes. This is diode. I want to show you the diode equation. Then later on we can go to the solar cell because solar cell is made of p-n junction. Uh-huh.
We are forwarding the bias
Uh-huh.
gradually.
Gradually.
If we forward it using the high voltage, 10 volts, 100 volts, what will happen?
Oh, if you bias the diode like 10 volts, 15 volts.
Yes. What will happen?
Yes, actually, you are a little bit ahead of me because I'm going to tell you, this is the equation, the 2 page later. 2 page, yeah. Because when we're doing the forward bias, then it will level up between 2 sides. Then it's become conducting. So you hardly feel the presence of the PN junction. It's conducting. It's conducting. However, if you put the reverse bias, it will increase the gap for electron and hole transport. So it's not conducting, almost non-conducting. So you will not see the very significant current develop with applied voltage. So that is the characteristics of the PN junction. All right, but I will repeat that. You are very good. You are very good. You are ahead of me. But I'm very successful because I induce the question from you. Okay. At the center is where the equilibrium condition is fulfilled. All right. So this side is N side, right? How do you know? How do you know this side is N side? Because Fermi level is close to the conduction band. Okay. The left-hand side is p-type. How do you know? Because Fermi level is close to the valence band edge. And they align. They are in equilibrium. If that is not in equilibrium, the Fermi level will not be aligned. All right? So for N-type semiconductor, since we are doing intentionally, artificially N-type doping, so there are a lot of electrons compared with holes. All right? For the P-type semiconductor, there are a lot of holes, but very little electrons. Right? So when we put in contact, what will happen? There are a lot of electrons, but you know, the higher the energy level, the less the electron population. All right? So just like black people, there are high score students and low, but the higher the score, the less student can get, right? So it's the same as in energy levels. At high levels energy, there are few electrons, but at low levels, there are a lot of electrons. All right? So for this level, low level electrons, since there's a barrier to prevent them from diffusion. So this low level electron cannot diffuse toward the p side. So they are blocked by the discontinuity. Not really discontinuity, the barrier. I should say the barrier. All right. Only those electrons with very high energy can diffuse back. However, the number of electrons diffused left-hand side will be the same as the holes diffused right-hand side. It will equilibrate. Has to be equilibrium. Has to be counterfeit exactly the same. Otherwise, there will electron flowing back and forth. Then we are rich because,
Immobiles.
yes, they have to be the same. All right. Also, for the holes, P side has a lot of holes, right? So actually, this diagram is for energy electrons. So you need to see the positive charge holes the other way. So the upper one means the lower energy, holes with lower energy. And the bottom one is a hole with higher energy. Only those holes with higher energy will diffuse toward the N side. But it will be counteract with another direction of hole diffusion from P side. And those with low energy, the hole with low energy, cannot overcome the barrier, so they are blocked by the p-n junction. So this is the equilibrium condition. So when we put p-n junction together, immediately when they put in contact, there will transient current occurring, maybe in like 1/1,000,000th of a second. Then it stopped. Everything the building width has all developed fully, and they become stable and also in equilibrium. So this is the equilibrium condition. Now let's go to the forward bias condition. The forward bias condition is to put an extra battery to connect to the p-n junction with positive side connect to the p and negative side connect to the n. Okay, so negative side connect to the n means I will increase the electron concentration toward the n side. So I will increase the energy level of n side with respect to that of the p side, right? You know, if I put a lot of people in a very crowded room, then I will induce stress, right? That means energy increases. That's exactly what happens. The same as when we are forward bias. I put even extra electron into n side, and I put extra number of holes in p side. So we are increasing their population. So their energy, the electron energy increases with respect to the p side. Also, the whole energy increases with respect to the p side. So the barrier actually reduces. So by reducing this barrier, now we have extra electrons that can overcome the barrier. So it can flow from n side to p side. And also, under forward bias, there will be extra holes that gain energy that can overcome the barrier and flow from p side to n side. So now it's conducting. And conduction direction is by diffusion. This is called diffusion current because the direction of a mobile charge movement is the same as diffusion. The electron is diffusing from n-type, whereas the electron concentration is high with respect to the other side. Flow from high concentration to low concentration. So this is called the diffusion current. So when we do the forward bias, it will induce the diffusion current, and it is conducting. Okay? So, have questions? I don't mind if you raise questions, all right? But if you didn't, you can raise your hand or call me if you really have questions. And okay, so for the reverse bias case, now we are biasing it reversely. So it's just the opposite situation of forward bias. We'll increase the barrier. So that all the electrons on the n side cannot overcome the barrier anymore. So those electrons cannot flow to the p side. But is there still current going on?
No.
Yes or no? Raise your hand. Yes. Very good. So there's still a little bit of current. Where? The electron is caused by the electron. Even though at p side they are very little electrons, but still electrons. They'll flow from this side to the other side without being counterfeit by counter react from the other side. All right? And also for holes, the same thing. Now, under reverse bias, there are no more holes on the P side that can overcome the barrier, energy barrier. So the hole cannot flow from P side to N side. However, there are always very little number, small number of holes in the N side materials. And at the time, there are no barriers. There are always no barriers. So these holes can still flow from N side to P side. So now there's still some current going on. But is this current the same direction as diffusion current? No, the opposite. Because this is just need to flow this side, this on this side. This is not a diffusion-driven current. This is called the drift current. This is called drift current. Drift current is driven by the electric field. They will drop from high energy side to low energy side. So this is driven by building field. So this is called the drift current. This is not the diffusion current. So we have two kinds of current. If the charge movement is the same direction as diffusion, then it's called the diffusion current. If charge movement direction is the same as driven by the built-in electric field, then it is called drift current. Why it's called drift current? There's still another level of meaning, because this current is not changing with bias. Because when you do the reverse bias, it just prevents those majority carrier from flowing to other side. But actually for this flow, it didn't change. You are not preventing this charge from flowing, the minority charge to flow to the other side. So the bias will not change the value of current anymore when you do the external reverse bias. They are constantly the same without affected by the external bias, because the mechanism is different. They just flow this way. Because actually this drift current is controlled by the concentration of electron in the P side and the concentration of holes on the N side. It's not really controlled by how strong the building electric field is. So the current will not be a function of building electric field. In turn, it's not controlled. It's not a function of externally applied field or bias. So it will keep the same, but very small, because minority carrier amount is very small. You can hardly feel it. So it's very small. All right. So again, I'm not going to use the handout that you just received until very late lecture today. So you just keep that for a while. I still need to finish the lecture handouts that you received yesterday. All right? All right. So let me review this idea again. We are almost there. We are almost there to get our PN junction equation. For forward bias, we induce diffusion current. All right? We induce diffusion current. And will the diffusion current increases with forward bias? What do you think? This is forward bias. If we increase the forward bias, we'll reduce the barrier. So will you think the current will increases with forward bias? If you think yes, please raise your hand. Okay, put it down. Huh? Current. Increase the current, yes. Do you think the forward bias will help the PN junction to induce increased current? Yes. Yes, of course. Yeah. But I still need to ask, right? What do you think? Has anybody think that if you are forward biasing the PN junction, the current will not increasing or even reducing? Anyone? No. Very good, very good. Because in the forward bias, you will increase the population of the electrons, also majority carrier that can overcome the barrier. So the more you bias, the more you get the diffusion current. Okay. So this, in forward bias condition, the current will increases with bias, and it induces the diffusion current. Basically, they are basically diffusion current. In reverse biased, they are normal diffusion current. All right, and current is very low. And this is not the diffusion current. This is called drift current because it is not dependent on the voltage. The amount of current is not dependent on the voltage. It is dependent on how much electron that will go to the depletion region and being guided to the other side. All right? Okay, so if you know this one, if you know this idea, then this is result will be reasonable for you now. That is, for forward bias, you have by increasing the bias, you have increased the current. All right? On the positive side, if I define this as positive, diffusion direction as positive, then it will be positive. At the reverse bias, there are currents, but this current is not big. All right? So sometimes we regard it as open circuit because current is very low. And it is not dependent on the reverse bias anymore. And it's negative charge, negative current. Actually, the negative and positive is defined by human. You can define the positive or negative in either way. But in this case, I define the diffusion current as a positive direction of the current. So the drift current will be negative. All right? And also, very important thing, at no bias. At no bias, that is in equilibrium. No bias, is there any current?
No.
No. If there's current, we are rich now. We don't have to worry about the renewable energy anymore. We just put PN junction there, there's current going on. Okay, so this will be the current behavior, characteristic behavior that for PN junction. And you have to make sure that this point has to go through 0 point. Also, there's upper limit of the voltage. There's upper limit of voltage. We cannot increase the voltage higher than this one. Why? Huh? Any student has answers for me?
Because after 0.7 the current will drop.
Almost there, yes. Because you induce a lot of current. You are reducing the barrier, right? This is N side, this is P side. When you put the forward bias, you are reducing the barrier. So there's more electron going on and going on. So will you be able to increase the Fermi level and the conduction band N side over the conduction band of P side? It's not possible. If that case is occurred, there will be no resistance. So the current will go to infinity. All right? Yeah. So there's always limits for this one. And the limit is controlled by the difference of the Fermi level. Actually, the barrier. We cannot overcome the barrier. We can always reduce the barrier, but we will not be able to overcome over the barrier. When we align to reduce the barrier to 0, then the current will go to infinity.
Yes.
Okay, that means this is a barrier, and it will not exceed the barrier. So there will be a limitation. Usually, for silicon PN junction, the barrier, it depends on the band gap. So usually the solar cell, this will around 0.7 volts. All right, but I'll go more detail afterwards.
But Doctor, experimentally, when we test this, when we just increase the voltage above 0.7, it has no effect on the current.
You cannot adjust to 0.07. Before you adjust to 0.7, then there's a lot of current.
Yeah.
Then you'll burn your. Well, usually there are resistance, right? Yeah. So it will counterbalance each other. So you will not be able to turn to 0.7 even.
Okay.
Because at that time, when you near diode the voltage near 0.7, you cannot feel there's PN junction exists. The circuit, inside the circuit, it's conducting. It's now like ohmic contact. It's not even, there's no resistance, hardly any resistance. Yeah. So you will not feel there's a presence of PN junction. All right? Okay, any question? So, okay. So this is a characteristic curve. We have to memorize this, right? So this can be used, PN junction can be used as to convert AC current to DC current, because it only allows one direction of current to flow through. So if you connect a diode to the outlet of the wall plug, using wall plug, it will become direct current, not alternating current. It only allows the certain direction to pass by, so it becomes DC from AC. Okay, so since diode has this function, so we use diode many places. Okay, so if you go to electronics store or accessories, sometimes you can find this, or your IC board, you can find something very small one. The large ones, small ones, like this. Actually, it's a PN junction, all right? And this is called a diode. So try to recognize, actually inside is PN junction, and there's a depletion region found at the interface, as we just mentioned about. And this is usually drawn in the circuit as this one. Have you seen that in the circuit diagram, electronic diagrams? The circuit diagram, you always see that. So make sure this triangle towards the direction this triangle toward is N. Okay? And also, there is a blocking on N side. Okay, that means the current can go only one direction. Yeah. What is the direction of current? You can test that by a positive charge. The positive charge can only go from the triangle side to the other side. It's like there's a channel here, there's a blocking here. So positive electron can only go through the funnel to the other side. But the positive charge cannot go from this side to here because it's very difficult to find the opening of the funnel. Right? And for negative charge, it's the opposite. So for negative charge, it is very easier to go from this side to anode, but it's very difficult to go from anode to cathode. All right. So this diagram is drawn respected to the positive charge, or respectively to the current direction. So we cannot think about the particle flow of electron. If you're thinking using electron, then this will be opposite. So it causes a lot of confusion for the student. But I think for you, you are fine. You are fine. You're just really talented students. Very good. Okay.
For negative, it will be the same circuit, but it will be from cathode to anode. Yeah?
Say again.
The same circuit, right?
Circuit, yes.
But the current will move from cathode to anode.
Current will move from anode to cathode.
I mean for negative.
Negative charge.
Yeah.
Negative charge will go from cathode to anode, even though the diagram is still the same. So you will only be able to understand the symbol by consider positive charge, even though the real moving particle is negative charge.
Yeah.
So it's caused a lot of confusion, right? Okay, so in order to recognize the polarity or the direction of anode and cathode, usually they will label a ring or a band at the cathode side, which is N side, right? Okay, so if you buy a diode from the store, electronic stores, you can test that with your multimeter. Okay, so if you didn't recognize this band, or you forget which band this will appear, which side will appear, you just test. If you put this, which side this is, N side or P side? N side. Very good. Yes, N side. So if you connect to the COM and you measure the resistance, right? You dial this to the function of resistance and put the positive to the other side. Then it will conducting or non-conducting. Very conductive. Very conductive. So the resistance shows almost zero. All right? Now, if you put that oppositely, then it is high resistance, hardly any current going through. So it's high resistance. The resistance is so high that exceeds the range that multimeter can handle. So it shows something that is error. Oh, sometimes you look like this. I don't know what this means, but sometimes it just shows error. Overload. Good, good. Okay, now I know. Overload. Overload, maybe. Okay, so this is an idea of drift current. Drift current is relatively insensitive to the height of potential barrier, as I mentioned earlier, right? So the diffusion, drift current is controlled by how many carriers that can flow into the depletion region. So they'll be driven toward the other side by the building field. So it is not depend on how strong the building potential is. It depends on how many carriers that can go into the depletion region. So it is not actually affected by the bias. Okay? However, for diffuser current, that is another case. If you increase the forward bias, you will increase the diffusion current. All right? And the diffusion current direction is opposite from the drift current direction. Okay, so we may have a break now for 15 minutes.
Yes.
Then now you already know. If you have no problem up to this point, you are in good shape. Now I can go to later on, it's very easy for you to go to the solar cell. Solar cell is actually so-called photodiode. you need to add the property of photo interaction with diode. Then you'll be able to know the mechanism for the operation of solar cells. So we'll show you how to draw the diode band diagrams at the beginning of the after 15 minutes. All right? Okay, any question? No, okay, now we break for 15 minutes. See you later. Start our lecture now. So I want to show you how to draw the band diagram for the diode under bias. All right, now we consider the forward bias. At equilibrium, you already know how to draw that, right? Yeah. Actually, there will be a depletion width, of course. So you draw, actually this width can be calculated, assuming that you already know how the value of depletion width. You can draw the depletion width as well as the conduction band edge, valence band edge, and for P side and A side. But make sure that the Fermi level is the same, at the same height. All right. And the Fermi level is actually controlled by the doping level. So once you know the doping level, you will be able to determine where the height of Fermi level with respect to P side or N side. All right. So this is very easy to construct. Now, I assume that you know how to draw that, even though I know you haven't drawn that before, but I assume that you know how to draw this. Then how to convert this equilibrium condition to the condition that is under bias. For the forward bias, we start by removing this transition area. Redraw PNN without transition portion. Okay, so something like this. We'll start from this. Now, if I forward bias with so-called VF, a VF value, bias that in a V voltage that called V forward, then I will raise the N-type side with respect to P side by QVF. See? Can you understand? I raise N side of Fermi level with respect to the P side Fermi level by a number which is Q times the voltage that is forward biased externally. All right? Okay. Then you need to, then the third one, since we are forward biased, so the depletion width will become larger or smaller? Smaller. Yes. Very good. So we need to bring that closer. Actually, you can still use this line, but since it's confusing, you just bring this to. There's a line you probably cannot see.
Yeah.
They're not shown.
Yeah.
They're not shown. Okay. You can still use this line as a reference, right? So you increase that, then there's a difference between here and here, the slope. So you just need to go until you touch this slope. Then it's about the right width that you are going to have in the forward bias condition. So see, you bring this up, then move a little bit closer. Like this line moves that. I'm not sure if I can change. Probably not a good idea of changing at this right now. It takes too long time. All right. So you imagine that there's still slope. There's still slope in this place. Then you just bring this closer until this one touches the slope. Right? bring that close, touch the slope. Then it's about the right width that you will get at forward bias. All right? Then after that, then you try to connect these two with a new slope. All right? Then since you raise the n-type n-side with the QVF, then the conduction edge barrier reduces from QV0 to QV0 minus QF. Okay? Okay? It's very straightforward. Then you can remove everything else. Then add up these labels on each side. Then you got the new forward band diagram for the forward condition. Right? Okay, how about the reverse bias? Very similar. Very similar. You remove the slope, transition region, the line for the transition region. Then reverse bias, you move down the n side QVR with respect to the p side. All right? So if VR is somewhere like this, you move down using Fermi level as a reference. You move down of Fermi level on the n side with respective to the p side. Okay? Then move level n side away from those p side. Now you have increasing. You should have increased depreciation width now, right? Mm-hmm. So you imagine like do you see the lines? You see the lines, very light one, very fake, very fake one. Okay? Because I just want to, I don't want to show you too clearly because there's really no lines. Okay, so you need to withdraw this side until you touch to the slope again. So for the third step, you withdraw a little bit. That means you increase the width to the slope. Then you can connect these two sides together. All right? And remove everything else. Now, your band edge barrier increases from QV0 to QV0 plus VR. And now you can remove QVR and put the labels for each side. Now you finish your drawing. All right? It may not be able to show. Is that show clear enough?
Is Q teacher
because I may do the overlapping to show this, so it may not be as clear as I shown in the projector, the screen. So if there are any questions, just let me know. Anyone who doesn't understand the procedure of constructing the p-n junction phase energy band diagram? Okay, should be very straightforward. Okay. Yes?
Only we are
To
neglecting the drift current.
drift current.
We are neglecting that current, or there are some benefits of that current.
Say again.
In reverse bias.
In
Reverse bias.
reverse bias, yes.
The current
The current,
almost are
almost drift current,
drift current.
yes.
We are always neglecting that.
Diffusion current,
No, I mean we are not
Always-
counting that.
without counting the drift current.
Yes.
Oh, we have to consider there's always drift current, but drift current is so small that is hardly,
All time will be small.
all the time, yes. Unless you didn't do a very great job of doing p-n junction, the leakage or the leakage path, then sure there will be a very high reverse current. Otherwise, ideally, the current is very low.
Yeah.
Okay.
I think it's considered as switch off.
Yes, yes, yes. Uh-huh.
Yeah.
That means even though you are switching off electronically, there's still current going through.
Yeah.
Uh-huh. It's just,
Slow.
yeah, very insignificant compared with forward bias. So they're still using current, but that doesn't matter because if you control that digitally, you need to just specify if I exceed certain level, then I treat it as 1. If it's less than certain level current, I treat it as 0. And you know the digital world is always 1 and 0, constructing the strings. So even though the low current, we can assume, we can define that at very low current, it is regarded as 0. Uh-huh. Okay, so after the construction of the energy band diagram, I will show you the diode equation. This is the purpose of this section. The current will be I equal I naught times exponential QV over KT. This is the power of exponential minus 1. Okay? So I'm not going detail about the equation. There's some derivative of the equation, but it takes several hours. All right, so I will not disturb you about this detail. So you just need to memorize this equation. I equal to I naught. This derivation can be found in any textbook of like semiconductor devices. So you don't have to worry about that. It's very easy to get. You can even go to Google website and find it. Yes. And if you cannot find it, look for me. I'll show you. If you are very patient about it, I can show you. Okay, so it's an equation like this, and you can expand this term to something more complicated, more details, but you don't have to. I know it's a very small number. It's a very small number, but in the forward bias, the exponential term will take effect. So even though this coefficient is very small, I will be very large. When very large number multiplied by a very small number, and it will eventually increase to infinity. Exponential will go to very high. Okay? And when V is negative, then this term will quickly drop to 0. So it's a negative value, I know, and not changing with voltage anymore, even though it increase the reverse bias. So actually, this difference is I know, I0. All right? And it will be, and when V is 0, when we have no bias voltage, then this term will be 1. 1 minus 1 is 0. So current is 0. All right? So this equation can explain forward bias, reverse bias, as well as under no bias. Okay, skip that. That is usually I ask my student to do the homework, but not for you.
Thank you.
Okay, so this is the equation again. So I just want to show you when it is in reverse biased, it quickly, when you increase the reverse bias, it quickly will saturate at a very small number. All right, this is negative I know. Okay, any question up to this point? Oh, very good. Very good. You're in very good shape. Have you learned this before? I believe so, right?
Yes.
Okay. So no wonder. No wonder. Now, I'm going to the next topic. What if the reverse bias going on, keep going on?
Yeah.
You break again, because no material can endure bias at very large value, right?
Yeah.
Eventually, it will break down.
It looks like this.
Yes.
Like that.
Oh, very good.
That's not me.
So this is called a reverse breakdown. Reverse breakdown, something like this curve, right? So we need to add the features, not only this one, and something that is not described by Diode equation. This is called the breakdown. The Diode equation is a simple equation, only explains this portion. But when we reverse bias to a certain voltage, it's a break, and it causes a lot of reverse current. So again, it becomes no resistance anymore. It becomes conducting, just like insulator. An insulator, you thought that is insulator is because your bias is not large enough. If you bias that at very high voltage, eventually it will conducting. That's what happens. The same here at the reverse breakdown. So forward bias, let's review here. Forward bias is set up like this one. You put the battery of positive side to P and negative side to N. That's forward bias. For negative or reverse bias, you put the positive of the side of battery connected to N and negative side connect to P. This is reverse bias. And if you keep this reverse bias voltage increasing to a certain point, then it will generate a current very fast, much faster than the increase of the current. You see? Drop down like very steep.
Almost 90 degrees.
Huh? Almost 90 degrees, right. Okay. So we want to know the mechanism of the breakdown. There are two main mechanisms for the breakdown. So you have to know this, because if you want to use diode as the DC-AC converter, you cannot bias it, reverse bias, exceeding the breakdown value. Otherwise, it's not adjusting, not transforming correctly. Okay? Okay, now I'm going to talk about the first mechanism of breakdown. That is called the Zener breakdown. Now you know under reverse bias what will happen in the band diagram, p-n junction, right? So on the left-hand side, it is unbiased condition, right? And for the right-hand side, it is in the reverse bias condition. The inverse bias condition, you will enhance the barrier. You enhance the barrier, reducing the current, right? So at certain point, your valence band edge on the P side will be higher than the conduction band on N side. That means the electron, they always feel the electron below the valence band edge, right? But they're almost empty compared with the electron at the at the valence band. There are a lot of unoccupied orbitals above the conduction band. All right? So when you reverse bias the p-n junction, at certain point, the valence band edge on P side will be higher than the conduction band edge. on n side. That means the electrons in p side has higher energy than the orbitals on n side. All right? So usually the energy will go from high energy to low energy, right? So, but something prevents them from transferring is a barrier. There's a wall transition region between two sides that electron cannot go from p side to n side. However, under certain cases, if the barrier is small enough, sometimes a phenomenon called tunneling occurs. Okay, we think electron is a particle, but actually it's a wave, right? It's a wave. So the wave can always penetrate through materials. It's just not 100% pass through, but they probably will pass through 1 out of 100 electrons. It's a ratio, all right? And depend on the width. If you have very narrow width, then you can go through a lot of electrons. If you have very wide width, the barriers, then very little amount of electron can pass through. This phenomenon is called tunneling. So this only happens when this barrier is in the nanometer range, or even smaller. So it will not happen in our scale. No, you're not going through the wall. You're not going through the wall because now our wavelength is very short compared with the thickness of wall. So the wavelength cannot pass through. But for very long wavelengths, it can pass through the wall. As long as the wave is longer than yes, like a radios wave, it can pass through the wall. But for us, we cannot. Now, this wall may be small compared with the wave function of the electron. So electron can still got a chance, some electrons still got a chance to be able to pass through. All right? So if we create this condition by reverse biasing, we might create a situation that this electron can tunnel through the barriers and causes breakdown. Now I induce the current. Oh, so at reverse bias, it's certain. Actually, if the reverse bias is not large enough, this will not happen. Because when the reverse bias is not high enough, the energy of electron on p side, the valence band, is still not high enough, not passing through the conduction band edge of n side. So the electron does not possess enough energy to be tunneling through. All right? This will only occur at very high, at reverse bias. That is when the electron on p side of the valence band is higher than the conduction band of n side. All right. So it's not occur immediately. You need to bias at certain reverse bias to occur. And also, there's also a limitation. The barrier width. The barrier width has to be very small. It's not usually happens. Not every case we will have a Zener breakdown because this only occurs at certain condition. When you doped the PN junction so that the width is very small. Okay, because the width is a function of doping, right? Right. Even though I didn't give you the equation, but you can think about that. It's a function. So the doping condition will determine if you can find the Zener breakdown or not. Usually, you will have a very high doping. If you have very high doping, then you only need to have a small depletion region to balance, to build the internal field to counteract with the diffusion of carriers. If you have a very low doping level, then you need to have a very large depletion region then to counteract with the diffusion flow. So usually for high doping case, then you have very sharp interface. That means you have very narrow depletion region. Then usually, sometimes this Zener breakdown will occur, right? So for Zener effect to occur, usually it will occur at heavily doped junction, all right? Then you need to have reverse bias with electron tunneling from P to N. Okay, this is one mechanism for breakdown. Okay, but there are certain requirements for the doping condition. So if you want to avoid the Zener breakdown, you cannot doping too heavy. You need to avoid the doping too heavy. Okay, so it's a little bit complicated here. Two parameters determine if the PN junction will tunneling or Zener breakdown occurs under reverse bias. Those two parameters are the width, depletion width, and the tunneling distance D. These two parameters are different. The depletion width, say this is a simplified band diagram, PN, and I just draw the slope. This slope representing the depletion width, right? So W is the width of the slope, like this one, right? W is from here to here, all right? So actually, in W, there are no mobile ions. So electron is only appear here, not here, not here, all right? Okay, so this is W. And what is D? D is actually here, the red one. D is the tunneling distance from this side, because there's all here, from here to here. This is real. Above this, they are electron energy higher than the N side. So really tunneling distance is this one. Okay, so for tunneling to occur, not only your D should be very small, but also your W should be also very small to occur. Okay, so you see, so actually this D decreases with reverse bias. D decreases with reverse bias. You see?
Yes.
Actually, you know, when you bias, the field increases. So this slope increases a little bit. I just exaggerate that so you can see the changes. It's not as that exaggerated case, but you can see the D did not increase. The D did not increase with reverse bias. It decreases. All right. However, the W increases with reverse bias. So actually for Zener breakdown to occur, you need to increase your reverse bias to a certain level, so that N-type, the valence band energy, is higher than the the valence band of P-type will be higher than the conduction band of N side. So you still need to increase some reverse bias. But in the meantime, when we increase the reverse bias, you increase the depletion width. So Zener breakdown should happen like several volts of a reverse bias. If it is not occurring in several volts of reverse bias, it will not occur anymore. All right? Because if it's not occurring at 7 volt of reverse bias, then if you keep increasing the reverse bias, it will increase the depletion width. So now you just deviate away from the tunneling condition. So this mechanism will not function anymore. Okay. So for this Zener breakdown to occur, you need to create an environment that when you do the reverse bias, the width is very small. That is when you dope very high, very heavy. Okay, so if you want Zener to occur, then you want to dope heavily. And if you don't want the Zener to occur, then you dope very lightly. All right? Okay, so very important thing is it only occurs at like several volts. And if not occurring at the reverse bias of several volts, say you are not occurring at 10 volts, then it will not occurring the breakdown as in Zener mechanism. Okay? Then, but still, if you increase the reverse bias, eventually they will break down. But it is going through another mechanism called avalanche. Then I'm going to talk about the avalanche. Avalanche is like a chain reaction. When you doped the semiconductor not high enough for Zener breakdown to occur, then you have very wide depletion width, right? And the depletion width will go even wider with increasing of reverse bias. All right? So, so now we have very wide, if the Zener breakdown did not occur, so we have very wide depletion width. And at this moment, only diffusion current will occur. So the minority carrier in P side is electron, will go from here to N side. However, because the field, the width is so high, so that electron can be accelerated. Electron is accelerated in the depletion region. So it is not moving down along with the slope. It is accelerating. Then suddenly it may collide with atoms in the depletion width. And previously there's no mobile charges. No mobile charge. Mobile charge means movable charge in the depletion region, right? But when this electron go into the depletion width with high energy, because it's accelerated by this electric field, so it increases velocity to certain energy, that when it will be able to transfer the energy in the collision and create electron hole pair. Okay, this is what happened in avalanche breakdown. It will have gained enough energy by the acceleration under the electric field, and this energy may cause the generation of electron hole pair in the depletion width. If that occurs, then this electron and holes will also move. The newly generated electron holes will also accelerate it in the depletion region. So electron will move also along with the previous electron. And the holes will move in another direction. All right? And it got accelerated also. So these holes may go the other way and gain energies and knock another atoms and create another electrons, secondary electron and holes. And this electron and holes, then electron will go this way and knock another one. So this will happen one by one, and depend on the generation probability. If the probability is low, probably this will just happen once and then come down without this avalanche phenomena to occur. However, if you keep increasing the reverse bias, you increase the width, and then you can increase the electron energies going through. Eventually, this will occur. So no matter if the semi-PN junction will have Zener breakdown or not, eventually they will break down. And if they are not break down through the Zener mechanism, they will eventually break down through the avalanche mechanism. Avalanche effect will always occur. All right? When you increase the reverse bias.
What's the main difference between this and the
Zener breakdown. Can you tell the difference? Difficult, right?
I know what the avalanche, but Zener, I didn't get it.
Zener is tunneling.
Means narrow.
Huh? The width has to be very narrow.
Yeah. And the avalanche should be large enough.
Very wide to accelerate the carriers. So it can knock another atom and create the electron hole pairs. Okay. And then a breakdown happens at low reverse voltage. And the avalanche breakdown occurs at high reverse voltage. Okay, so this may occur as chain reaction. So one knock and creating two accelerated creating four. So it get add up. Then at some point, when you increase reverse bias, then it will create a lot. When you increase to certain voltage, then the avalanche started. Then create a lot of current, then that you cannot control. Then it's breakdown. Okay. So we can use a very simple equation to describe this phenomenon. The P is the probability of electron holes traveling through the depletion width that can generate another electron and hole pair. The probability. All right? So if we consider electron and holes that traveling through the width, actually electron and hole has to travel, and they add up. The distance that they travel is exactly the same as the width, depletion width, right? Because no matter where the electron hole are generated, electron will go this way, hole will go the other way. So their traveling distance add up is equal to the depletion width. Can you understand? No matter where the electron hole is generated, the electron will always go this way, while the holes will always go this. Let me show you here. This is a simple. This electron hole pair is generated. Once generated, under the influence of field, electron will always go to the right, and hole will always go to the left. So the traveling between this depletion width. Once the hole joins this neutral region, then you cannot tell the holes. It's not accelerated anymore, because only in this region there will be electric field to accelerate. So the avalanche will only occur in depletion region. So the traveling distance for hole and electron that generate at the same place is exactly the distance of the depletion width. Because hole traveling from here to here, electron travel from here to here, so these two paths add up is equal to the depletion width, right? So if we consider electron and hole, the impact probability is the same. So we can always consider the generation event as the going through the path of the depletion width. If we consider electron holes, that the capability of generating electron hole pair by electron and holes are the same, then we can consider the particle that traveling through the depletion width, how easy or how difficult they can generate electron and holes. So the P means during the traveling of particles, no matter it is electron and holes, during the path distance of traveling of particles in the depletion width, how easy or the probability it can generate another electron hole pair. All right? So if there is no avalanche mechanism occurs, then you input one electron, then it will be one electron coming out. So N in will be equal to N out. All right? But if there's a probability, a very small probability, much less than 1, even much less than 1, probability of creating electron holes, that is when you increase the reverse bias to a certain level. You have like 1/1000th of a probability that will be able to creating another pair, electron hole pair in the during the traveling of depletion width. Then you are not creating only one piece, one pair of electron holes, but you are creating P plus P squared plus P cube, etc. Because the first event of electron hole pair generation will induce the secondary electron hole pair generation. So you need to add up all the possibilities. So finally, the electron coming out is the summation of N times 1 plus P square plus 3 cube, etc. All right? A little bit complicated, but I think you'll be able to understand if you think about that after the class. All right? So the multiplication factor is N out over N in. That is this factor. And from the elementary school, not high school will be able to know when P is less than 1. Even P is less than 1, you will be able to get the... Do you know this equation? No. You have to know. This is summation of the... How to call this? Huh?
What series?
Huh?
What series?
Boa series? Maybe, I don't know. I know now this form. If you add, it's infinite series. The infinite series of the same multiplication coefficient.
Yeah, it's I think product series.
Yes, product series. Yes, okay.
I guess.
So you'll be able to get this for infinite series, summation of infinite product series then you'll be able to get this one. Very old time, like several years ago, right? You probably forget now. Okay. So actually, the current coming out is more than the current that you input. So you induce a lot of current. That is why, you see, when you in is very small current, but you generate a very high current at certain voltage. And mathematically, you can use this model to model the multiplication factor. It is when breakdown, when V very close to the breakdown, then this multiplication will occur significantly. So we can use this simplified model to simulate this breakdown situation. And this power is around 3 to 6, depending on the materials, right? Okay, so now if you want to distinguish between Zener breakdown and avalanche breakdown, this is categorized here. Impact for avalanche breakdown is impact ionization. It's impact. It's being accelerated and gain enough kinetic energy and knock the impact the material, and rather than field ionization. Field ionization is a wave going through the barrier. It's called field ionization. Now for avalanche breakdown, it's carrier multiplication. There's no carrier multiplication in Zener breakdown. Zener breakdown, 1 and become 1 is no multiplication event. The peak electric field within W increases with increased doping on the more lightly doped side of junction. Actually, it just want to show that width is a function of doping. If you dope the other one side much lighter than the other side, the depletion width will develop at the more lightly doped side. Okay, but this probably I didn't mention in the class, so you didn't know about that. I intentionally omit this part because this goes too detail. We may not be able to teach you in the 5-day workshop. So forget about this. Forget about it. This is more detail. Okay, so this is the diagram for 3 kinds of semiconductors for the breakdown current. This usually the diagram is for which kind of breakdown? This is for avalanche breakdown because the range for doping is very low. It's very low. You know how say this just give you an idea of a doping level. This is the unit of centimeter square per centimeter square. If you dope the material 10 to the 15th per centimeter cube, centimeter cube, is that a high doping or low doping?
Low.
15 is very high, right? But actually it's very low because you need to compare with crystal structure. Usually in the crystal structure, in a volume of centimeter cube, there will be 10 to the 21 or 22. This order of atoms inside the cube, centimeter cube. 22 or 21 order, all right? So 15 compared with 22 is like very small amount. Like you only have 1 doping in millions of atoms, right? So you only replace 1 silicon atom by phosphorus in millions of silicon atoms. So actually the doping is very low. Okay? Just show you an idea. If you want to be a solar cell scientist or semiconductor engineering, you have to have the feeling of the order of this property. So usually at this range, the avalanche breakdown dominate. But as your doping concentration increases to 17 and 18, at that time we consider the doping to be in the medium. Not really that high, because we can dope the semiconductor to like 19, 10 to the power of 19. At this doping concentration, 19 compared with 21 or 22 is still 1,000ths or 100ths, right? So at this doping level, it's still not altering the crystal structure of silicon. So still, but at that time, it may be degenerated. At that time, it's very possible for certain semiconductors. And it's usually is conducting. But as a region, we consider now is becoming high, towards the high end of the doping level. If you dope at 20, 10 to the 20s, then this dopant will precipitate and form another phase. Then it is not called doping anymore. It's called alloying. It's not doping because it will cause it exceeds the solubility of silicon, so the contaminant will precipitate and form a phase by itself, or a compound of phases, not belong to the previous silicon structure. So this is where the avalanche occurs. And you can see that this is a trend. As the doping concentration increases, the breakdown voltage reduces. Right? All right. So if you want the breakdown, want to avoid a breakdown, actually you cannot avoid the breakdown, but just want to, it happens at very high reverse bias. You want to increase the doping or reduce the doping?
Reduce it.
Reduce, yes. Here, you can find it. If you lower the doping concentration, you can increase the breakdown to 1,000 volts without being breakdown. Okay? And also, it is also a function of band gap. And as you can see, germanium has very small band gap. So you can easily create electron and hole pairs, right? Very small energy, you can create electron hole pair. So it's more easy to break down. So the breakdown voltage will be low compared with semiconductors with wide band gap. So you will be able to see this breakdown voltage as a function of band gap of materials. And also, when the doping concentration increases, you'll see the breakdown voltage reduces at a certain point. Now, Zener breakdown plays some role and dominates at high concentration, doping concentration ranges. Okay, so this is also something that I asked my students to do in Taiwan, back in Taiwan. But actually, because I didn't mention about this into detail, but this is easy. I just gave you the numbers and you just need to plug in this equation. But I didn't tell you which one is which, right? I didn't give you too many details about this. So if you are interested, you might try to see if you can calculate the value. All right? So, but I can foresee maybe there's some problems because the parameters that I give you here is not exactly the parameters I shown in the equation. There'll be some other, like Einstein relationship to relate this parameter with the parameters that's shown in the equation. Right? So try to see if you can do that. But if not, no problem. No problem. Just forget it. Okay. So you are the first group that is going to conduct the experiment. So now we have 2 panels in series connection. So as I mentioned earlier, when the solar panel is connected in series, there will be serious problems. So it's easy to remember.
It's now serious.
Excuse me? Excuse me. And
We're trying to keep the current equals to zero.
yes, actually you are going to record the voltage, this
the
column,
current equals
the value of this column, and the current
Yeah.
in amplitude, this one. So actually right now it's very easy. Instead of connecting in series parallel, we just need to switch this dial. We switch to series. No? Then it's series connected.
Yeah.
Okay? Series connected, you go to turn counterclockwise. This is extreme. And if you go clockwise, I go to another extreme, this voltage is 0. So it's pretty much VOC, highest voltage is 28 something. All right? And at 28 something, the current is almost 0. Then if you go to another extreme,
The voltage 0.
voltage 0, and the current is 0.0363. So it's about saturation. It's a saturation current. It's this side. So, oh, I'm sorry. So now, so remember this current. So if you want to go this stream, you try to increase the current from 0.47 to gradually to about 63. Then you can go faster.
Yeah.
Yes, good. Okay, now I think you understand what I'm talking about. Okay, try to do that. Now make sure that in the series connection. Okay. Good. Yes. And then.
مرة الأولى خلط قراءات، المرة الثانية رصينا واحدة في خلط قراءات. احنا الحين في جروبكم بندرس ايش الافكتس لما يكون برا. بناخذ قراءات لما يكون هذا انشري وبعدين نسوي ريد نغطي. بنشوف. اللي احنا في النهاية بيطلع لنا كذا. ففي البداية احنا لازم نحدد المينيموم والماكسيموم. أول ما يتأخر نروح للماكسيموم. بدنا نلاحظ هنا هذا بدنا نطلع 5. أوكي 50 فولت مثلا. فلو قسمنا ال 50 فولت على مثلا فترات مثلا 5 10 فهمتوا علي؟ فهذا يعني لو خذينا مثلا يعني بس تطلع لنا نقطة واحدة ونقطة واحدة من قبل ونقطة واحدة من قبل. الكيف ما بيطلع لنا كذا. فعلى أساس إنه يطلع لنا الكيف سموث هذه الفترة احنا بناخذ أكبر عدد من القراءات. وبعدين في هذه الفترة اللي هي فترة إنه يكون ثابت بناخذ عادي 15 ما في مشكلة يعني. بس هذه الفترة على أساس إنه نوصل لنفس الكيف. فجيد حد قدم وحد سجل
مرشد يلا
بعدين اشياء
صح اعطاكم ده. ففي البارالل الفولتج نفسه والكرنت وش قسم ولا مجموعة
مجموعة
الكرنت مجموعة ايوه. فالحين نبدا التجربة. كويس للصفر كويس الماكسيموم ومن الماكسيموم ابدا ارجع.
اوكي يعني ابدا من هنا
ايوه روح للماكسيموم. لحظة على الفولت
دور
هذا المكتب خلاص موجود.
انت الحين لما تنقص شوف الكرت. حاول انه الكرنت ما ينزل نزله او ما يرفع. اوكي. فاذا ارتفع يعني فترخص قراءتك. اوكي. يعني شوي ينقص قراءتك عشان ما تتوقف. حلو. اوكي.
اوكي هنا وقف.
وده شيء وده شيء وده شيء وده شيء 5 7
هذا الشيء واحد مثلا
Perfect, yes.
اذا تنفع زيد عن المتابعين.
This needs to be here.
No, this is only. I don't know how to control anyone else. But you got it?